Hello everyone, I'm Faisal Hussain, currently studying mechanical engineering at London South Bank University. Today, we're going to discuss on vector calculus. So before that, we would like to understand what is a vector field, why do we need to learn this, its application, and then why we shifted to gradient, divergence, and curl to understand the vector field in a better way. Right. So basically, a vector field is a way to represent how a vector quantity, it can be anything like a velocity, force, which like has a magnitude and a direction, or a wind that changes across space. Space means basically location. So over here, as you can see, there is a refrigerator, and underneath this is a simulation of that airflow. Now you can see this airflow, these arrows, this indicates the airflow in the refrigerator and these colors. So you can see this, it shows the speed of the air. So this overall simulation, it helps engineers or the designers to see fast jets, the slow zones, and the circulation of the air that may affect the cooling performance of the refrigerator. So basically, it's all done by the simulation. Next, as you can see, this is a wind map of the UK where you can see some directions over here. I hope you can see it. So the directions is going upwards, and this side there's some colors. So basically, this map, it it shows that how the wind is moving across the country, and you see the direction as well. And over here, the light colors, this means the wind is not that much strong, but the darker colors means the wind is strong enough. So basically, it through vector field, we can analyze this type of simulation or describe this type of reports. Next, so basically, we have given a vector field, which is y I cap minus x j cap. Now we need to consider four random positions, and we want to insert those positions in a paper, let's say. So uh, we'll take four coordinates, for example, 0, comma 1, 1, 0, 0, minus 1, and minus 1, comma 0. And based on that, we're gonna insert these values. So for example, for A, which is x is 0 and y would be 1. And if you insert these values to this equation or this vector field, you will get I cap. Similarly, for B, you will get minus j. For C, at this point, we get minus I, and then for D, we get j cap. And if you plot it into a paper or a graph, it will look similar like this. So basically, you can see it's kind of a clockwise direction, right? Now, if we want to make a better visualization of this graph, we would like to take another point. So for example, over here, take a random z point, let's say 1, comma 1. And if you insert this point into this equation, you will get I cap minus j cap. And then the graph would look kind of like this. So as you can see, as we know, I cap, it defines the horizontal plane, and the minus j cap, let's say minus j cap, it means that it's going downwards vertically, right? Z point, this is 1 comma 1, and it will be a resultant of these two vectors. So this is the resultant. I defined it with Vz, and yeah, it gives us a more accurate graph. And finally we will get this type of thing. So like if we plot more and more points to make a complete picture. So as you can see, this is circulating in the clockwise direction, right? Next, let's say another vector field, which is 2x I cap plus 2y j cap. Similarly, we'll consider four positions and we will get these values. And then for the better accuracy, we will take another point, which is this one. And then we can get something like this. So as you can see, this is 2 cap, I cap horizontal direction, J cap upward or vertical direction, and this VZ is the resultant of it. So as you can see, this arrow is going away from the center. This is the center or origin of the graph. So it's going away from the graph, and this is a source. If we complete this graph, it will look kind of like this. So it's moving away from this from the center of this graph, and it's a source. Again, another example could be minus 2x I cap, minus 2y j cap. And similarly, we'll take four positions, random positions. And at one point, we will get something like this, which is going towards this origin, right? So this is a sink. Now, as I mentioned, that vector field, it helps to indicate like either the system can be source or sink or like let's say solenoidal. But as you see that it takes a bit moment of time understand either it can be a source or sink. So there is some time constraint. To make this easier, or like to simplify this analysis, we typically use gradient, divergence, and curve. So these are the vector calculus. So before starting this topic, I would like you to understand what is a source, sink, and solenoidal. So source means something is generating, right? It could be anything like something, let's say mass or temperature like heat, any charge, fluid, any fluid, and is it generating or not? So this means all these are type of source. Now, talking about sink, that means something is being removed from the system or something is being absorbed from a particular system. And solenoidal means there will be no source and no sink. So basically, it will just only circulate. And in that case, the divergence becomes zero. We will talk about it a bit later in this video. So this basically the basic concepts of source, sink, and solenoidal. Try to keep it remember. Now, we will talk about gradient now. So what does gradient means? It means that how quickly something changes and the reason behind it. So basically it's like slope and it measures the rate and direction of the change in a scalar field. And as an output for gradient, we always get a vector field. Now, this is how we define gradient. So basically this is the Nebel operator, we can say, and this is the like a partial differentiation. We have covered this topic in last week. You can see that. So this is the way that we write the gradient formation, where delta by delta x I cap, it represents the change field in I direction, or like I cap direction. I cap means the horizontal direction. For this, it represents the change field in j cap direction, and this one represents the changing field in k cap direction. Now, if we assume that there is a function, let's say function t, let's say is x, y, z, then if we plot it over here, so we will get something like this. And as per the rule of partial differentiation, what will we get? So with respect to x, over here, we get yz I cap. With respect to y, we will get x, z, j cap. And with respect to z, we will get xy k cap. So this is very basic and very easy for you, I know, guys. Now, we'll see one example here. We have been given like phi x comma y, and the function is x squared plus y squared, and we have been told to find its gradient. Now, we can either write like this, like grad, then phi, or we can use this operator, then phi, and then we can set up this formation like this, right? And then similarly, we will insert this value. So with respect to x, what would be its partial differentiation? So 2x plus 0 with respect to x, right? So it would be 2x I cap plus with respect to y, we'll get 2y j cap, and with respect to k, look, there are no terms of k in this equation. So the whole thing will be 0 k cap, right? So the answer will be 2x I cap plus 2y j cap. Next, let's say for this example, we have been given this function, we have to find out the gradient, and we have been told to find the gradient vector at a particular point. So this is 1, 1, 1. So we will set up the formation first and we'll do the partial differentiation. So with respect to x, where y and z is constant, and we will get similar like this. And with respect to y, we will get this, and with respect to z, we will get xy. And then we will insert all of this equation into our main formation. And as you can see, we'll get something like this, right? Now, as this point is mentioned, 1, 1, 1, we will now substitute these values into this equation, and then we will calculate it, and you will get something like this, 6i cap plus 7j cap plus k cap. So this is the answer, or this is the gradient vector for this particular function at this point. Now, we'll look into divergence. So it tells us how much a vector field leaves or enters at a particular point. And as an output, for example, for gradient, we get a vector field as an output, right? But for divergence, we get a scalar field as an output. So since it's a scalar field, definitely the operation would be a dot product, right? So here, if you do the divergence, and if you get something positive value, if it comes positive, that means it's a source. If it comes negative, it would be a sink, and if it turns 0, it would be a solenoidal. We'll see some examples now. For example, this example. So we have been told to find the divergence, and yeah, similarly, we'll set up the formation and then this function, and we'll do the dot product, right? Or dot multiplication. So here, delta by delta x I cap will go with this x I cap. For this operator, delta by delta y cap, delta by delta y j cap, it will go with y j cap. And then delta by delta z k cap will go with 0 k cap. I mean k with k, j with j, and I with I cap, right? And we have simplified the equation like this, the whole operation. And then we will do the partial differentiation, which is 1 plus 1 plus 0, as there were no k terms in this equation. And we get positive value, right? Since it's a positive, that means it's the source. Now, at the very first of this video, I have told about those graphs, right? Like you have to consider 4 points and then plot it into a graph, and you need to check either it can be source or sink or solenoidal or what. Even we understood their circulation process, like clockwise or anti-clockwise. So basically, it took a bit moment of time, right? But for this type of for this operation like divergence, it instantly tell us that if it's a positive, that means it's a source. So we don't need to include, or like we don't need to make any additional graph to identify it. So that's the key advantage of this vector calculus, like gradient, divergence, and curl. We will see another example. Similarly, this one, we have been told to find the divergence, and yeah, we get a negative value over here. So that means it's a sink. Then for this example, all are the same process. They're very easy and hopefully easy to understand for you guys. So yeah, we have been told this function y I cap minus x j cap. So we'll set the formation, we'll do the partial differentiation, and ultimately we got 0 over here. Since we got 0, that means this is solenoidal, so there will be no source, no sinks. So nothing will generate, nothing will absorb from the system. So it will flow around only, right? Now, curl. We need to understand how a vector field will spin or rotate either clockwise or anti-clockwise. So because of curl, we can easily find it out. So if the curl is 0, that means there will be no rotation and no twisting. So basically it would be irrotational vector field. And if it's not 0, it has a particular value, then it means there will be some source of rotation or twisting, and it would be a rotational vector field. Let's see some examples, guys. So over here, we have been given a vector field, and we need to determine the curl of this field. So we will do the cross product this time. For divergence, we did the dot product, but for curl, we will do the cross product. So we'll set up the formation, cross product, and this function, and we'll do the determinant now. So that's the determinant formation of this problem, and we will solve it like this. So for example, in terms of I cap, right? So this column and this row will be eliminated. So we'll do the multiplication between delta by delta y times 0 and minus delta by delta z times minus x. So something like this. Then for j cap, we will eliminate this column and this row. So what will be delta by delta x times 0 minus delta by delta z times y, right? And similarly for the k cap plus k cap, and this column and this row will be eliminated. Then we will get delta by delta x times minus x minus, over here, minus delta by delta y times y. So we'll do the partial differentiation here. And ultimately, we obtained minus 2k cap. Now, what does it mean? Since it's not 0, it has a particular value. That means there will be some source of rotation. So this is a rotational vector field. Now, if we use the right-hand rule, so k cap, we'll just consider k cap. K cap is basically anti-clockwise, like positive k cap is anti-clockwise, but since it's negative, it would be a clockwise rotation, something like this I've shown here. So that is how you can define the rotation of a particular vector field. We'll see another example for this. Let's say this vector field. We will do the determinants first, like this, and in the same way, we'll do the cross multiplication, and ultimately we got 0. So 0 means if the curl is 0, that means it is irrotational, right? And the final example of this video is something like this. We have been given this problem. We need to find the curl of this vector field, and we will set up the determinants and then do the cross multiplication like this. So these are very easy. Just focus on the partial differentiation. You need to be careful on that. And ultimately we got y minus x k cap. As you can see, this is not 0. This has some particular values. It can be any values, like y can be, let's say, 5, or like x can be 3, anything. So it has a particular value. That means it's not 0. So this is not rotation, not irrotational. That means this is rotational. So you have to be careful on these words, right? So yeah, that's all for today. I hope you enjoyed the lesson, and if you have any questions, please let us know. And thanks for watching. Thank you very much.